In a high-concurrency production environment, we often witness a paradoxical failure. Adding more CPU cores and increasing the thread count actually leads to a decrease in overall system throughput. This is the notorious Global Interpreter Lock, or GIL, in action. For over 3 decades, the GIL has acted as a serializing bottleneck, ensuring that only one thread executes Python bytecode at any given time. In a multi-core era, this creates massive lock contention, where threads spend more time waiting for the lock than performing actual computation. From an IT strategy perspective, this represents a significant architectural debt. While it guaranteed thread safety and simplified memory management for legacy systems, it has become an invisible ceiling that prevents Python from fully leveraging modern hardware parallelism in CPU-bound tasks. This bottleneck isn't just a performance lag, it's a fundamental structural constraint that dictates how we scale enterprise-grade Python applications. But why was this bottleneck allowed to persist for so long? We will uncover the hidden trade-offs that kept the GIL alive until now. Mastering the removal of the GIL is not just about faster code, it is about evaluating the long-term sustainability of your technical stack. In this lecture, we will dive deep into Python 7.79 and the free threading capabilities introduced in Python 3.14. Our objective is twofold. First, to understand the low-level mechanism of how the interpreter now handles thread safety without a global lock, and second, to develop a strategic framework for assessing the readiness of enterprise C extensions. If your system relies on NumPy, SciPy, or custom C+ integrations, the transition to a GIL-free environment is not automatic. It requires a rigorous audit of thread-safe memory patterns and ABI compatibility. By the end of this session, you will be able to determine exactly when and how to migrate your mission-critical systems to Python 3.14 to unlock true multi-core throughput. This knowledge is what separates a standard developer from a runtime architect who can navigate the complexities of modern language internals. But before we look forward, we must understand the technical gravity of what we are leaving behind the reference counting system. To understand why Python 7.79 is revolutionary, we must look at the 30-year evolution of Python's memory management. Since its inception, Python has relied on a simple but effective reference counting mechanism. Every time an object is referenced, its counter increases. When the reference is dropped, it decreases. While elegant, this system is inherently thread unsafe. Without the GIL, 2 threads could simultaneously modify the same reference count, leading to memory leaks or catastrophic crashes. For decades, the GIL was the necessary evil that protected this fragile process without requiring expensive per-object locks, which would have slowed down single-threaded performance by up to 50%. This design choice made Python the most accessible language in the world, but it also locked us into a single-core mindset. In the field, we call this a local optimum, a solution that is perfect for the current state, but prevents reaching a higher peak. Python 7.79 finally breaks this cycle by redefining how we handle these counters. Does this mean we are sacrificing single-threaded speed for multi-core gains? The answer lies in the shift from experimental to official support. The transition from Python 3.13 to 3.14 marks a critical maturity phase for the language. While Python 7.03 introduced the capability to disable the GIL, it was largely experimental and presented a nightmare for library maintainers who had to manage 2 different builds. Enter Python 7.79. This proposal specifically addresses the C-API compatibility problem, providing a unified path for the ecosystem to transition without fracturing the community. In 3.14, we see the shift from "can we do it" to "how do we make it standard?" This involves new biased reference counting and memmalloc integration to replace the overhead of the GIL. From a management perspective, 3.14 is the version where you should begin your pilot projects, as it provides the stability guarantees that enterprise systems require. We are moving from a world of cooperative multitasking to preemptive parallelism at the runtime level. But don't be fooled, simply turning off the GIL isn't a silver bullet. You need to understand the internal mechanisms that replace the lock, which is exactly what we will deconstruct in the next chapter on free threading mechanisms. In the traditional C Python architecture, the global interpreter lock acted as a coarse-grained shield, ensuring that only one thread could manipulate Python objects at a time. To remove this lock in Python 3.14, the core development team had to rethink the very foundation of reference counting. Enter biased locking and immortal objects. Reference counting is inherently thread unsafe. If 2 threads increment a counter simultaneously, the data becomes corrupted. Biased locking allows an object to be bound by a specific thread, avoiding atomic overhead for local operations. Meanwhile, immortal objects' global constants like none or true are now marked to bypass reference counting entirely. This structural shift moves us from a single lock world to a sophisticated environment where memory safety is managed at the individual object level rather than the runtime level. It is a fundamental evolution of the Python memory model that aligns with modern multi-core hardware. But memory safety isn't just about counting, it's about where those objects live in the heap, which brings us to the allocator. When we remove the GIL, the standard memory allocator becomes a bottleneck. In a free-threaded environment, multiple threads frequently request and release memory segments simultaneously. To handle this without massive contention, Python 3.14 fully integrates memmalloc, a high-performance, thread-safe allocator originally developed by Microsoft. Memmalloc utilizes a tiered structure, thread local shards for small allocations, which allows threads to manage their own memory pools without locking against other threads. This architecture prevents heap corruption, a nightmare scenario where two threads write to the same memory address. From an architectural standpoint, this shift to memmalloc is what enables the high concurrency scaling we see in modern benchmarks. It represents a move towards zero contention memory management, a critical requirement for any enterprise-grade multi-threaded runtime. Efficiency is key, but adding these protections adds a tax. How much does this tax weigh compared to the old GIL during the actual execution of your code? The bytecode interpreter is the heart of Python. In a standard build, the instruction pointer moves through opcodes with the absolute certainty that no other thread is modifying the current frame state. In a threaded build, every single bytecode operation must be re-evaluated for thread safety. This involves bytecode specialization, where the interpreter replaces generic instructions with specialized, thread-safe versions based on the execution context. Python 3.14 optimizes this by using a deferred safety model. It identifies hot code paths and applies more aggressive optimizations while maintaining internal consistency. This process ensures that multi-threaded execution remains predictable and correct without requiring the developer to manually lock every variable. However, this safety comes at the cost of instruction overhead. We are essentially trading a single massive lock for thousands of tiny, highly optimized checks. This leads to a fascinating trade-off in execution speed, but wait, how does this granular locking compare to the old, coarse-grained approach when we look at the raw numbers? To understand the strategic shift PEP 703 and 779, we must compare fine-grained locking against the old coarse-grained GIL. The GIL was simple, one lock to rule them all. It was incredibly efficient for I/O-bound tasks where threads spent most of their time waiting for the network or disk. However, for CPU-bound tasks, it was a hard ceiling. Fine-grained locking, as implemented in 3.14, allows multiple threads to run in parallel, but it introduces a locking tax on every operation. If you are doing heavy arithmetic in multiple threads, fine-grained locking is a massive win. But if your code is highly serial and spends all its time on a single core, the extra overhead of managing these tiny locks can actually make it slower than the GIL version. This is the conundrum of parallelism that every architect must weigh when deciding to enable free threading. Theory suggests massive gains, but let's look at the hard data from the 2026 Performance Lab benchmarks to see the real-world impact. The data from 2026 production environments confirms a revolutionary shift. In CPU-bound multi-threaded tasks such as image processing, local LLM inference, and large-scale data transformations, Python 3.14 demonstrates a 2x to 4x speedup on standard 4-core systems. When we scale to 16 cores, we see near-linear performance improvements for workloads that were previously GIL locked. This isn't just a marginal 10% improvement, it is the difference between a task taking an hour versus 15 minutes. These benchmarks represent the efficiency frontier of the new Python runtime. However, achieving this requires your code to be structured correctly to avoid state contention. We are finally seeing Python move from a scripting language performance profile to a high-performance runtime profile capable of saturating modern server hardware. Wait, if it's so much faster on 4 cores, why did early versions of this feature actually make single-threaded scripts run significantly slower? Every major architectural change has a cost. In the early experimental builds of Python 3.13, removing the GIL resulted in a single-thread penalty as high as 40%. This meant your legacy code ran nearly half as fast just to support a feature it wasn't even using. In Python 3.14, the team has achieved a massive engineering feat by reducing this overhead to a mere 5-10%. This was achieved through the bytecode specialization and biased locking we discussed earlier. While 10% might still sound like a loss, the trade-off is the ability to unlock the other 90% of your CPU's potential. For enterprise applications where single-thread latency is critical, this 10% gap is the current migration tax. Most modern services, which are inherently concurrent, will find this a price well worth paying. But we must remain realistic about where the benefits stop. We have the speed, but there's a mathematical limit to how much we can keep gaining, a law that every architect must respect. As an IT strategist, I must remind you of Amdahl's law. It states that the speedup of a program using multiple processors is limited by the time needed for the sequential fraction of the program. Even if we remove the GIL entirely, if 20% of your code is inherently serial like global state updates or single-threaded I/O, you can never achieve more than a 5x speedup, no matter how many cores you throw at it. In real-world Python applications, the performance gains often plateau once you hit the limits of memory bandwidth or the serial nature of the C extensions you are using. Free threading is not a magic wand for bad architecture. It is a tool that rewards developers who design for parallelism. The runtime is ready, but your libraries might not be. This brings us to a critical warning. The runtime may be free of the GIL, but your legacy C extensions are often still built with the assumption that the GIL exists. In the next chapter, we'll dive into the C extension trap where your code might actually crash. In the world of Python 3.14, the removal of the global interpreter lock is not an unconditional gift. For years, C extensions have implicitly relied on the GIL to protect their internal states from data races. To bridge this gap safely, CPython introduces an explicit opt-in mechanism. Developers must now signal that their extension is free threading ready by using the PyMod GIL not USD flag within the module definition. This is not just a formality, it is a declaration of thread safety. If you are building a high-performance library in 2026, failing to include this flag means your code remains shackled to the legacy execution model. We must understand that the interpreter's priority is stability over speed, and it will not assume your C code is thread safe unless you explicitly prove it through this API. But what happens if you forget to add this flag or use an older library that hasn't been updated yet? The answer lies in a defensive mechanism that could silently compromise your performance goals. The most dangerous aspect of the Python 3.14 transition is what I call the silent reactivation. When the Python interpreter starts in free threading mode, it scans every loaded C extension. If it encounters even one single module that does not carry the PyMod GIL not USD flag, the runtime immediately and automatically re-enables the global interpreter lock. From a strategic standpoint, this is a safety mode fallback. The interpreter prioritizes preventing a catastrophic crash over maintaining multi-threaded performance. The problem is that your application will continue to run without any visible error, but your multi-core scaling will vanish. In a production environment, this can lead to confusing performance regressions where adding more CPU cores yields zero benefit. You must implement runtime checks to monitor the GIL status to ensure your environment hasn't regressed into legacy single-threaded execution. This leads us to a critical question. Which major players in the Python ecosystem are actually prepared for this transition right now? In the professional landscape of 2026, the readiness of your stack is defined by your dependencies. Major scientific libraries like NumPy and SciPy have been at the forefront of the PEP 703 migration, refactoring their internal C and Python code to handle fine-grained locking. However, the ecosystem is vast, and many niche or legacy libraries remain GIL dependent. When planning an enterprise migration, you must conduct a thorough audit of your dependency tree. One incompatible library at the bottom of your stack can invalidate the performance gains of your entire architecture. We are currently seeing a tiered readiness where core data science tools are stable, but specialized visualization or proprietary hardware interface libraries are lagging behind. This necessitates a strategic checklist approach before flipping the switch on free threading in a production cluster. Now we understand the risk of silent failure and the ecosystem status. How do we actually bridge the technical gap for our own custom extensions? The transition to free threading introduces a major divergence in the Python ABI, or application binary interface. In Python 3.14, we effectively have two different types of builds, the standard build and the free-threaded build. These two are not binary compatible. You cannot take a wheel compiled for a standard Python 3.14 interpreter and load it into a free-threaded one. This creates a significant challenge for CI/CD pipelines. As a technical lead, you must manage dual build targets, ensuring that your automated systems produce and test both variations. The free-threaded ABI often includes additional overhead for thread-safe reference counting, which we discussed in the previous chapter. Understanding this binary wall is essential for distributing Python packages in 2026. Having the right binary is one thing, but how do we prove that the internal logic of these binaries won't crash under high concurrency once the GIL is removed? Detecting thread safety issues in C extensions requires a shift in our testing methodology. Standard unit tests often fail to catch race conditions because they don't provide enough thread contention. In the professional field, we utilize tools like Thread Sanitizer, TSAN, and Valgrind to monitor memory access patterns during execution. When migrating an extension, your workflow should involve running your existing test suite under a free-threaded build with TSAN enabled. This will help you identify Heisenberg's bugs that appear and disappear randomly depending on thread timing. Furthermore, tools like PyTextDist should be used not just for parallel test execution, but to deliberately induce conditions in the target module. In a high-stakes enterprise environment, "it works on my machine" is no longer sufficient. You need a verifiable trace of thread-safe memory operations. If we do find a thread safety issue, what are the modern patterns to fix it without bringing back a global lock? The final stage of migration is refactoring. For decades, C extension authors used the GIL as a big hammer to protect global variables and shared buffers. In 2026, we replace this with explicit synchronization primitives. This means moving away from global state and towards thread local storage or C11 atomic operations. Instead of locking the entire interpreter, we use fine-grained mutexes that only protect the specific data structure being modified. For example, replacing a simple integer increment with an atomic fetch and add ensures that multiple threads can update a counter simultaneously without corruption. This transition from implicit safety to explicit concurrency is what separates a legacy developer from a modern Python systems engineer. While these low-level changes empower developers, they also shift the architectural burden to the enterprise level where we must decide when and where to deploy this new power. In the next chapter, we will examine how to position these architectural shifts within a corporate strategy. In the enterprise world, we don't adopt technology just because it's new. We adopt it when the ROI is clear. For decades, Python's answer to CPU-bound tasks was the multiprocessing module. While effective at bypassing the GL, introduced a significant tax, the serialization and deserialization of data between processes, often using pickle. With the arrival of free threading in Python 3.14, we transition from process-level isolation to true shared memory parallelism. This is a game changer for machine learning inference and heavy data processing where large feature vectors no longer need to be copied across process boundaries. However, don't be fooled into thinking every workload benefits equally. Small, short-lived tasks might actually see a performance regression due to the increased overhead of fine-grained locking and specialized memory allocators. We must categorize our workloads based on data size and computation density to determine if the migration is architecturally sound. Does this mean the era of multiprocessing is finally over, or are there hidden costs in memory management we haven't considered yet? When evaluating the shift from process-based isolation to free threading, the most critical metric for enterprise architects is the memory footprint and the complexity of state management. In the traditional multiprocessing model, each worker process has its own private memory space. This provides a robust safety net. A crash in one process doesn't kill the others, but it consumes massive amounts of RAM for duplicate library and shared data. Free threading flips this script. By sharing a single heap, we can drastically reduce the memory overhead, which is a significant factor when running high-density containers on Kubernetes. However, this efficiency comes with a thread safety tax. Developers must now implement explicit synchronization using mutexes or atomic operations to prevent race conditions that the GIL previously suppressed. In a large-scale enterprise codebase, this transition requires a rigorous audit of shared state management. But beyond memory and safety, there is another subtle factor that affects user experience: the predictability of response times, which we will examine next. In high-frequency trading or real-time bidding systems, average latency is a vanity metric. The real enemy is tail latency, specifically the 99th percentile jitter. Under the legacy GL, threads often suffered from the convoy effect, where a single long-running computation blocked the entire runtime from switching contexts, leading to unpredictable response spikes. Removing the GIL directly addresses this architectural bottleneck. With free threading, the runtime can leverage multiple CPU cores to handle concurrent requests and garbage collection cycles independently, leading to a much smoother latency profile. This predictability is vital for maintaining service-level agreements in microservices architectures. We are moving away from a world of stop-the-world interruptions toward a fluid, concurrent execution model. However, removing the global lock introduces new types of contention within the memory allocator itself, specifically around memalloc structures. Now that we understand the why and the where, let's look at the strategic roadmap for safely landing this technology in production. A transition this fundamental cannot happen overnight. As enterprise consultants, we recommend a 4-year phased adoption plan starting from 2025. The initial phase involves canary testing, where free-threaded builds are deployed to non-critical internal tools to identify edge cases in proprietary C extensions. By 2026, as Python 3.14 matures, organizations should focus on shadow pipelines, running production traffic through threaded environments without using the output for live users. This allows for a direct comparison of stability and performance. The goal for 2027 and 2028 is selective migration of high-throughput services that are bottlenecked by CPU performance. Finally, by 2029, we expect the ecosystem, including major vendors like AWS and Google, to offer first-class support for free-threaded runtimes. This gradual approach minimizes risk, while ensuring that your technical debt doesn't accumulate during this paradigm shift. But how do we actually see what's happening inside these parallel threads during the transition? Observability is the lighthouse of enterprise architecture. When moving to a free-threaded environment, your old profiling tools might become your biggest blind spot. Traditional profilers that relied on the GIL's predictable context switching will fail to capture the nuances of true hardware parallelism. We must shift our stack to tools like VisTracer, which can visualize thread contention, or Austin, a sampling profiler that provides high-frequency insights with minimal overhead. In a multi-core execution environment, the bottleneck moves from waiting for the GIL to waiting for a specific mutex or cache line contention. Therefore, your profiling strategy must include hardware-level metrics and lock analysis. You need to be able to identify which specific shared resource is causing threads to stall. This layer of the stack is where performance wins are actually realized in a post-GIL world. Despite these sophisticated tools, senior management will still have one recurring question: what happens when things go wrong in the middle of the night? Risk management is the hallmark of professional IT strategy. The primary concern with free threading isn't just the code you wrote, but the millions of lines of third-party dependencies your enterprise relies on. If a critical vendor library isn't thread-safe, a free-threaded build could lead to Heisenberg's bugs that are nearly impossible to reproduce or debug. To mitigate this, every deployment must have a GIL re-enablement or process fallback toggle. Since Python 3.14 allows for both build types, maintaining a dual-stack CI/CD pipeline is essential. You must ask, does our cloud provider support the experimental free threading flags? And is our rollback procedure tested for data consistency? By treating free threading a high-impact infrastructure change rather than a simple version upgrade, we ensure business continuity. This concludes our deep dive into the architectural positioning of Python's most significant evolution. In our final chapter, we will synthesize everything we've learned to look at the future of the Python ecosystem toward 2030. As we conclude our technical journey into Python 3.14, we must synthesize the three pillars that define this transition. First, thread safety is no longer a luxury provided by the runtime. It is now a fundamental responsibility of the application architect. The introduction of biased reference counting and mymalloc-based memory management means we can finally utilize multiple cores, but only if we respect the new synchronization primitives. Second, C extension compatibility remains the biggest hurdle. The ABLS future is coming, and existing libraries must adapt to the new thread-safe internal APIs. Finally, workload selection becomes critical. Not every script needs free threading. Low concurrency I/O tasks might actually see a slight regression due to locking overhead. This paradigm shift requires us to move from a global lock mindset to a granular concurrency model. We are witnessing the most significant structural change in Python's history since its inception. But the GIL's removal isn't the only performance lever moving in the 3.14 ecosystem. There are other gears turning in the background that you must account for. Free threading does not exist in a vacuum. It is part of a multi-pronged offensive against Python's performance bottlenecks. While PEP 733 removes the execution bottleneck, the JIT compiler, evolving through PEP 659 and 744, addresses the sequential throughput of the bytecode itself. When you combine a JIT-enabled runtime with a free-threaded environment, you get a system that is not only parallel but also inherently faster at the individual instruction level. Furthermore, the development of subinterpreters, governed by PEP 6884, provides an alternative isolation model for those who prefer shared nothing parallelism over shared memory threading. Understanding how these three technologies, free threading, JIT, and subinterpreters interact is essential for modern system design. You might use subinterpreters for isolated task workers while utilizing free threading for heavy data processing within a single interpreter instance. This modularity is what will allow Python to dominate the next decade of AI and data engineering. With these three forces combined, Python is essentially being reborn as a high-performance runtime. But what does this mean for the person making the final architectural call? From an enterprise architectural perspective, Python 3.14 is a point of no return. We are moving away from the era where we simply waited for hardware to get faster or wrote it in Rust. The strategic directive for 2026 is clear. Python is now a first-class citizen for high-concurrency, CPU-intensive workloads. This change reduces the language tax previously paid when building large-scale ML pipelines or real-time data processing systems. However, this power comes with the price of complexity. Architects must now enforce stricter coding standards regarding state mutation and thread synchronization that were previously ignored due to the GIL's protection. The decision to migrate should not be taken lightly, but staying on the GIL-constrained versions will eventually lead to technical obsolescence as the ecosystem shifts its optimization efforts toward free-threaded builds. We are moving from a world of single-threaded safety to multi-threaded efficiency. Knowing the strategy is one thing, but what exactly should you do when you step into the office on Monday morning? To conclude, here is your immediate action plan. First, audit your critical C extensions. If they rely on the GIL for internal state protection, they will crash in 3.14. Second, start experimenting with the disable GIL flag in your CI/CD pipelines to identify race conditions early. Third, evaluate your current use of multiprocessing. Many tasks currently using separate processes to bypass the GIL can be refactored into lighter weight threads, significantly reducing memory overhead and IPC latency. Fourth, monitor the ready for no GIL status of your core dependencies like NumPy, Pandas, and PyTorch. The ecosystem is in flux, and being an early adopter requires a robust testing framework. Finally, update your internal developer training to include modern thread synchronization patterns. This is not just a version upgrade, it is a fundamental shift in how we build high-performance software with Python. This marks the end of our deep dives, but the beginning of a new era where Python's only limit is the hardware you provide.